Hi, today we're going to talk about some of the recent changes in the virtual NVMe implementation in SPDK based upon VFIO-user. As a brief refresher, VFIO-user is a socket-based protocol for implementing remote device servers. So we can see in this diagram, we have a VMM emulating a guest VM and a virtual NVMe PCI device, and that's implemented over a VFIO-user socket, with the server being inside the SPDK process and an implementation of a virtual NVMe controller within the lib nvmf library. So over the past year, there's been a large amount of changes both in libVFIO-user, the protocol, as well as the implementation inside SPDK. The focus has been on performance and scalability in general, but in this talk, we won't cover some of the other VFIO-user work, such as Changpeng's VirtIO support. First thing I'm going to talk about is multi-reactor support. So in general, for an individual NVMe controller, we would like to be able to pull the submission queues on more than one CPU to improve scalability. However, until recently, this was a problem because we need to unmap guest memory. And for that to happen, we need to be sure that that memory isn't currently being used by any I/O. For obvious performance reasons, we don't want to take any mutexes or anything in the fast path. So we need a fast solution to allow us to do this. The solution was introducing the idea of quiesce callbacks. And this allows the device implementation in SPDK to ensure that all I/O is quiesced at the point of that callback. And then the VFIO-user library is able to alter the memory map and be sure that none of the I/O handling is happening for that area of memory, and it avoids the need for any of the locking in the fast I/O path. And as an additional benefit, this easily allows us to scale across multiple CPUs because we have no mutex locks or anything like that in the fast I/O path. However, this only works well in polling mode at the moment, and we'll talk about that later. Another big change relatively recently is support for live migration. So now if you have a VM that's using a VFIO-user-based device, you can live migrate that to a different system. So one of the things we needed to implement for this was the tracking of page writes by the device itself. We need to keep track of those dirty pages so we know that we have to send them across to the destination. And we've implemented an API within libVFIO-user that SPDK uses. And this API itself is, again, lockless, and we've minimized the amount of atomic operations it has to do to record these dirty writes. And we also use the quiesce callback for live migration. So in the final stop and copy page, for example, we use the quiesce to ensure that all I/O on the emulated device has been stopped. And finally, we capture device state to send to the destination. Another recentest change was Rui Chang's implementation of IRQ suppression. The insight here is that if the device driver within a VM is actively reaping the completion queue, then it doesn't need an IRQ to notify it that there's new entries in that queue. It will just see those naturally. So what that means is that if we have a batch of I/O that we're doing all the completions for, we may not need to send any IRQs at all, and that can greatly increase performance in some situations. If we later discover that in fact we need to fire one of these suppressed IRQs, we can do so later on, but it still massively reduces the number of guest IRQs that are actually fired. And this isn't yet enabled in interrupt mode. That's some pending work we need to do as well. We've also made a bunch of different micro optimizations to the code based mostly upon looking at profile data. The main focus of these has been upon reducing the amount of CPU time that we spend, and also making sure that the CPU doesn't stall on things like barriers and unnecessary memory reads. Most of these have been relatively small changes to either CPU utilization or overall IOPS, in the order of 1 to 3%, but of course, all these things add up over time. I just want to talk a little bit about SPDK interrupt mode. So this is effectively unrelated to device interrupts. The best way of thinking about interrupt mode is that it switches from a polling reactor to an event-driven reactor. In other words, we have a bunch of file descriptors that we register with an epoll loop, and everything that happens is in response to one of these file descriptors becoming ready. So for the VFIO-user NVMe implementation in particular, there's two main events that happen. The first is an MMIO doorbell write coming from a guest VM. And in that case, we need to wake up and poll the corresponding submission queues for any new requests, submit them to the underlying BDEV layer, and then go back to sleep. And then the other side is completions. So in that case, the underlying BDEV has completed the request, and it needs to wake us up, and we need to post the completion status to the NVMe level completion queue, and then go back to sleep again. So why would we choose to run in interrupt mode rather than polling mode? Well, there's a few different reasons. For example, it can be the case that you don't necessarily want to burn at least one CPU core all the time. Even with a CPU frequency governor, that's still going to potentially lead to wasted CPU cycles. This is especially true in a configuration where we have more than one SPDK instance. For example, we may want one SPDK runtime per VM. And in that case, it doesn't really make sense for all of those SPDK instances to be polling all the time. So when it comes to the virtual NVMe implementation of VFIO-user, in general, the performance in poll mode is pretty good overall. But in interrupt mode, there's still some work to do. And we talk about some of the things where progress is still needed now. So shadow doorbells. So this is one of the major performance improvements we implemented a while back to improve interrupt mode performance. And this actually comes from the NVMe specification. The idea is with a shadow doorbell that instead of having to do a VM exit from the guest every single time we write to a doorbell, we can avoid most of those. But before SPDK is about to sleep, we need to rearm the device so that the guest driver does MMIO writes, and that becomes an FD which will wake us up. And under some loads, despite the implementation of shadow doorbells, we still see a lot of MMIO writes happening, and those correspond today to a VFIO-user socket message. And we can actually end up in a situation where QEMU and SPDK can't keep up. In one test, we saw a pending message list that was 500,000 entries long, which is obviously not going to work very well. So we need a way to coalesce and reduce the MMIO writes. One possibility is a protocol extension to actually coalesce the writes into fewer messages, which does work quite well. There's an ioregionfd proposal, which would allow us to do this as well. But we've been working on an alternate approach called shadow ioregionfd that Thanos is now going to describe in some detail. Thank you.
Let's take a closer look at what happens when the guest writes to an NVMe doorbell. The write is trapped in KVM. KVM returns to QEMU, then QEMU calls into the VFIO-user client, which sends the VFIO write message to SPDK. Because PCI writes are posted, control returns to QEMU and then back to KVM, which resumes the guest. In SPDK, once the VFIO-user receives the message, it calls the bar0 region callback, which copies the write to the doorbells and then returns to SPDK, which eventually processes the request. The solution we produce to avoid having to send a VFIO-user message for each MMIO write is a mechanism we call shadow ioregionfd. This mechanism is an ioregionfd, which is kicked whenever a guest physical address is written to, except that the value being written, which is the doorbell value SPDK absolutely needs, is not discarded, but instead is written to a piece of memory private between KVM and SPDK. This piece of memory is the actual doorbells in SPDK, which SPDK passes to QEMU and in turn QEMU passes to KVM when configuring the ioregionfd. This memory, which we call the shadow memory, is not visible by the guest. With shadow ioregionfd, KVM fully handles the MMIO write. The VM exit is not avoided, but we do avoid having to switch to QEMU for it to send the VFIO-user message. Now let's see what happens when the guest writes to the doorbells and shadow ioregionfd is used. The guest writes the doorbell and traps into KVM as before, but now KVM writes the MMIO value to the shadow memory, kicks the eventidx, and then continues executing the guest. Now, let's see how shadow ioregionfd helps to improve performance and CPU efficiency. In the left graph, we compare CPU utilization using FIO with and without shadow ioregionfd. By keeping the number of IOPS fixed, we see that shadow ioregionfd consumes 5 to 10% less CPU. But shadow ioregionfd not only increases CPU efficiency, it also enables the use of additional reactors. Without a shadow ioregionfd, a write to a doorbell whose assigned poll group is not the one also handling VFIO-user messages would result in the VFIO-user poll group waking up and then having to kick the poll group the submission queue is assigned to. Using a second reactor without shadow ioregionfd results in lower performance than using a single reactor. On the right graph, we see the benefit of using a second reactor. We see that shadow ioregionfd achieves almost double the performance of the non-shadow ioregionfd case in higher I/O depths. Another optimization we did to improve CPU efficiency in interrupt mode is to remove one level of equal weight. SPDK creates equal instances, and the resulting equal FT is passed to another equal instance. Therefore, when the higher level equal weight returns, a second level equal weight is used to identify which equal instance is ready. This mechanism allows threads to be migrated between reactors, which is essential for implementing load balancing. However, load balancing is not always needed. For instance, in NVMe, the guest statically maps queues between vCPUs. Therefore, we can do the same static mapping between queues and reactors. By removing the second level equal weight, we hook the FT directly to the first level equal weight, thus saving a system call. There are still a lot of areas to explore that could potentially help to improve performance. Adaptive IRQs are not yet enabled for interrupt mode, and we've seen adaptive IRQs do help increase performance in poll mode. We still need to push on upstreaming of shadow ioregionfd, as in addition to lowering CPU utilization and enabling multiple reactors, it also enables us to use a single ioregionfd for all the submission queues that belong to poll group, and not having to poll at all dormant queues, as the Linux driver initializes all available queues but only uses as many queues as vCPUs. Another area we looked at is to keep shadow doorbells enabled for as long as possible, which means rearming them just before we go to sleep. This led to lower performance, which is surprising, as in theory the longer shadow doorbells are enabled, the more we approach poll mode, which should achieve higher performance. We need to follow up on this. Also, for SPDK apps that need timers, it is possible to avoid using timer FT by using a heap for timers, thus saving a system call. This is the end of our presentation. Thank you.